Hello, Math 201. Welcome to today's lecture on 3.10 derivatives of inverse trig functions. And so let's remind ourselves of what an inverse trig function is. And so the terminology, sometimes we call it arcsine or sine inverse. That's what this -1 here, sine inverse of x. This is the inverse sine function. And so what do we mean by inverse? So remember from your geometry day or your, I don't know, pre-calc days, the sine function looks like this, right? It's this red curve right here. That's what y equals sine of x between -pi/2 and pi/2. The inverse function is the function that flips it if you flip the y and the x. So here's the line y equals x. And if you reflect this red curve over it, you get this function right here. And so what it does is it takes in the output of the sine function and spits out the input. And so sine takes in an angle, spits out a ratio. Sine inverse takes in a ratio and spits out an angle. And so for instance, if sine of pi/2, sine of pi/2 is 1, that means sine inverse of 1, if you go to 1 on the x, oh, that's supposed to be up to there, sine inverse of 1, if you plug in the ratio 1, it spits out the angle pi/2. That's the idea of the inverse sine. And so sine inverse of x equals theta if sine of theta equals x. Those are equivalent statements. And so remember, an inverse function is if you plug in a function into its inverse or the inverse into the function, it just spits out x. And so that's what the main idea of an inverse function is. And so remember, the key warning is that sine inverse is not the multiplicative inverse. It's not 1 over sine. This is not what it is. It's just the inverse function. And so it takes in a ratio and spits out an angle. And our goal, and so this is, we learned what the derivative of that function is, but today we want to learn the derivative of this function, the sine inverse function. And it will be intimately related to the inverse or to the derivative of the sine function. And so I'm going to really quickly go over where it comes from, but you'll not be tested on this derivation, but I just want to show you for prosperity's sake. So if I want to find the derivative of sine inverse of x, I can use the fact that sine inverse of x equals y, if and only if, taking the sine of both sides, sine of y equals x. And now this is an implicit function, so I can do implicit differentiation to both sides. Implicit differentiation on the left-hand side, we take the derivative of the outside function, which is cosine, times the derivative of the inside function, which is dy dx, and the derivative of x with respect to x is just 1. And so what we're left with is that the derivative of sine inverse of x is just dy dx, because dy dx is what we want to solve for, right? That is, if sine inverse of x is y, dy dx is the derivative of sine inverse of x. And so solving for dy dx, we get that dy dx is 1 over cosine y. This is technically true, but it's not enough. We want the derivative dy dx in terms of just x. And so using the fact that y is equal to sine inverse of x, we could plug that in right here. And then we get 1 over cosine of sine inverse of x. But this is gross, and we don't want to stop there. And so what we're going to do is we're going to use a little trig. And the idea is if you drew a triangle, you draw a little triangle with side lengths x, angle is y, right? Because y equals sine inverse of x. So that means the ratio of x over 1 is sine of y. And so that's the angle y. This is x over 1. And we want to know what cosine of that angle is. We want to know cosine of this angle y. And so cosine is going to be whatever this side length is over 1. But what is this side length? Well, by the Pythagorean theorem, s squared plus x squared equals 1 squared, which is this equation right here. Solving for s squared, we get s squared is 1 minus x squared. Taking the square root, we get square root of 1 minus x squared. Therefore, the cosine of this angle is 1 square root of 1 minus x squared over 1. Therefore, plugging that all in, we get that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. And this is true for all x values between -1 and 1. If you plug in anything bigger, it will not exist. And then you can't plug in -1 or 1 either, because the derivative would be undefined, which makes sense if you look at this picture. There's no tangent line when x equals 1, right? It's a vertical tangent line. And when you plug in x equals -1, it's also a vertical tangent line. So for anywhere in between those values, it's given by this equation, right? here. A quick alternate proof, you can use the fact that cosine squared plus sine squared equals 1. And then solving for cosine, you get plus or minus square root of 1 minus sine squared. But sine squared y is just equal to x because sine of y is equal to x. And so you get cosine of y is square root of 1 minus x squared. So you could do that too. At the end of the day, though, we get this rule. The derivative of sine inverse of x is 1 over the square root of 1 minus x squared. So we just add it to our rule. Adding the chain rule, if there's an inside function right here, then doing chain rule, it's 1 over square root of 1 minus that function squared, and then times the derivative of that function, right? That's the chain rule. So for instance, sine inverse of ln of x is going to be 1 over, and then square root of 1 minus ln of x parentheses squared. So this is a little thick. And then times the derivative of ln of x, which is 1 over x. And so that's a quick little example of how we can use that. And we can do a similar game for tan inverse of x, right? Tan inverse of x, if y is tan inverse of x, then that implies taking tangent of both sides at x is tan of y. Taking the derivative of both sides with respect to x, we get secant squared of y dy dx equals 1. And so solving for dy dx, which is the derivative of tan inverse x, you get 1 over secant squared y. And the way we're going to get secant squared y in terms of x is remembering that cosine squared theta plus sine squared theta equals 1. That's the Pythagorean identity. Dividing everything by cosine squared, we get 1 plus tangent squared equals secant squared. Therefore, secant squared is 1 plus tangent squared, or secant squared y is 1 plus tangent squared y. But tangent of y was x, right? That was our original assumption, that tangent of y is x. And so plugging this guy in right here, we get that secant squared y is 1 plus x squared. So plugging that all in, we get that the derivative of tan inverse is 1 over 1 plus x squared. This is a super important derivative that we use all the time and will be really important in Calc 2 as well. So let's record all them. The 4 most important ones I circled right here. You need to know the derivative of sine inverse of x, the derivative of tan inverse of x, and then similarly their partners, so cosine inverse and cotangent, and they're just the negative versions of these guys. The tan inverse and cotangent inverse are defined for all x values. The sine inverse and cosine inverse are only when x is between -1 and 1. So let's do a quick little example. Let's say we're given this function, f of y is equal to cotangent inverse of 2 over y squared plus 4, and I want to take the derivative. So I want to find f prime of y, which is the derivative with respect to y. I need to take the derivative of the outside function, which is -1 over 1 plus that thing squared. And so it will be -1. This is going to be really gross to write, but 1 plus, and then this whole inside function squared, which is 2 over y squared plus 4. Oops. Y squared plus 4 squared. And then times, now I need to times by the derivative of the inside function. And the derivative of this inside function, well, let me do this kind of scratch work on the side. Let's call this function right here u of y. So u of y is going to be 2 over y squared plus 4. What is the derivative of that function? Well, we can just do the product rule, right? Or the quotient rule. The quotient rule says low d high. So y squared plus 4 times the derivative of the high, which is 0, minus high d low. So 2 times the derivative of the high, which is 2y, all over low squared, y squared plus 4 squared. Simplifying that, we get -4y over y squared plus 4 squared. And so this right here is what's going to be multiplied right there. And so maybe I'll even circle that. Whoops. So that is going to go right here. And so what does this end up equaling? It'll be -1 over 1 plus 2 over y squared plus 4 squared times the derivative, which was -4y over y squared plus 4 squared. And you don't have to simplify it. I won't ask you to simplify. That's totally a reasonable answer right there. And so that's an example of a derivative we can do. All right, and now let's do an example of a word problem that you can do with these. So shadows in a ballpark. Let's say we have the sun is descending behind a 150-foot wall, and that you're standing S feet away from that wall, and you make an angle of theta with that, and then L is the distance from there to the top of the wall. We want to express theta as a function of the shadow length. We want to see how far the shadow is changing with respect to theta. And so what is a relationship? Well, this triangle really helps us out here, right? There's a relationship between theta, S, and 150. And that relationship is tangent of theta, right? The tangent of that angle is equal to opposite over adjacent, which is 150 over S, where S is the shadow length. And so now we want to compute d theta ds when S is 200 feet. And so how are we going to do that? Well, we can take d ds of both sides, right? So let's take d ds of both sides. Tangent of theta equals d ds of 1. I'm going to do it right as 150 s to the negative 1. To take the derivative with respect to s of this, you take the derivative of tangent. And what's the derivative of tangent? Well, we know that it's tangent, or that's secant squared theta, and then times d theta ds. And then that's going to be equal to, taking the derivative of this with respect is going to be negative 150 s to the negative 2 by the power rule. And then we can solve for d theta ds. And what will that be? D theta ds is going to be negative 150 s to the negative 2 over secant squared theta. And we want to, and rewriting that in terms of s, remembering that from our derivation before, that secant squared theta is the same thing as 1 plus tangent squared theta, but tangent is 150 over s. And so this would actually just be, let's think about that for a second. That would be, maybe the easier way to do that. Yeah, that's fine. So this would be equal to negative 150 s to the minus 2 over, and then 1 plus tangent squared theta. But that's equal to negative 150 s to the minus 2 over 1 plus, and then tangent theta is 150 over s. So this would be 150 over s squared. So then the final answer would just be to plug in 200 for s there and there. And so d theta ds, when we plug in s equals 200, would equal negative 150 times 200 to the negative second all over 1 plus 150 over 200 squared. And again, we don't need to simplify, just leave it like that. And so that is how fast the angle is changing with respect to the shadow length. When the shadow length is 200, it's going to be decreasing pretty quickly. All right. The final thing we're going to do is we're going to talk about derivatives of inverse functions in general. There's actually nothing special about the trig functions, or like we did last time with exponential functions. We can do this with any function. If you have a function of x is equal to y, which is just our standard way of saying function f takes in x and spits out y, well, that's equivalent to saying the inverse function takes in a y value and spits out x. So doing the same derivation as before, if we take the derivative with respect to x of both sides, we get that the derivative of f inverse evaluated at y times dy dx is equal to 1. And then solving for this piece right here, we get that f inverse derivative evaluated at y is 1 over f prime of x. Because this dy dx is f prime of x, remember? So y'all recall, because dy dx, that is f prime of x, right? That's from this step right here, taking the derivative with respect to x on both sides. dy dx is just another way to say f prime of x. And so it's 1 over f prime of x. And so how do we use this? Well, you can plug in a value for x and plug in a value for y. And so if x naught, y naught is a point on our function, that means if you plug in x naught here, it spits out y. Then you can plug in this y value right here into the derivative of the inverse function, and it'll just be 1 over the derivative evaluated at that x value. Here's a picture to kind of see what I mean. So if this is our point on our function with this tangent line, then the corresponding point on the inverse function, because y and x are switched, is y naught x naught, and its tangent line will have been reflected over that line. And so it'll just be 1 over this slope. So it's 1 over the slope that you get right here will be the slope at that point. And so in general, if you want to know what the without even having to calculate what this derivative is, you can figure out what this numeric value is by just plugging in 1 over the derivative of the original function evaluated at the x value. And so let me do an example to show you this, because this is this can be kind of confusing, but let me show an example. So here's a function that's not easy to calculate in its inverse function. It'd be very difficult to calculate. And let's say that this point is a point on that function, which it is. If you plug in 1 for x, it spits out 2, right? 3 minus 2 plus 1 is going to give us 2. And we can find the inverse function. Sorry, we can find the derivative of the inverse function evaluated at the y value 2 without finding f inverse by using this formula right here. So f inverse prime at 2 by definition is evaluated as 1 over, and then it's f prime evaluated at the x value, which is 1. And we know what f prime of x is because we have f of x right here. The derivative is very easy to calculate. The derivative is just 9x squared minus 2. And so that implies that f prime of 1 is going to be 7. And so this all implies that f inverse, the inverse function's derivative at 2, if we want to know how that inverse function was changing at the value 2, it's going to be 1 over 7. And that's how you do it. And so that's actually very useful because sometimes calculating inverse functions, for instance, for this function, calculating its inverse function would be very difficult, but we can calculate its derivative very easily by leveraging the fact that the derivative, the regular derivative of this function is not hard. All right, that is all you need for this homework. And yeah, you should be ready for the midterm. All right, take care.